What I'm going to be talking about today is electromagnetic innovations in cold cathode gauge technologies for analytical applications. And by that, I mean analytical chemistry applications. My goal today is just being the CTO for pressure measurement within MKS Instruments. I kind of want to give you a little bit of a sense of what goes into developing a product line. And in this particular case, we're going to be talking about a product line that is very well suited for analytical chemistry instrumentation applications. And kind of put you in my shoes and let you walk in my shoes a little bit while we go through all of these. So as an outline, I'm going to talk a little bit about vacuum science and its connection to chemistry. We will very quickly move on to the inner relationship between vacuum technology and analytical chemistry. And with analytical chemistry, depending more and more on instrumentation, right, to perform its analysis. And with vacuum being so important in that particular industry of vacuum instrumentation. Here at MKS, we like to talk about vacuum technology surrounding different technologies. And today we're going to be talking about how vacuum surrounds analytical instruments. And of course, because I'm on the pressure measurement side, we'll be talking about how we surround the chamber with vacuum measurement instrumentation or pressure measurement instrumentation. The focus is going to be on the MKS series 900 of vacuum gauges, which is very well suited for analytical instrumentation. It's not the only thing it's good for, but it's just a very, very well fitted, as you're going to see, based on the requirements of the industry for that particular application. And what I'm going to do is I'm kind of want to walk you through the way in which this line was developed. We started with at the beginning, right, when we started the line, focus was on rough vacuum instrumentation. We managed to play with MEMS technology early on at that point, and that helped a lot in the development of the product line. But then later on, as we tried to extend the product line into high vacuum, which is essential nowadays for vacuum instrumentation, things got a little more challenging as we ran out of MEMS options to use to make products smaller, and we had to start relying on ionization gauge technology. So I'm going to talk about some of the early successes and later surprises that we got as we worked on incorporating cold cathode gauge technology into the Series 900 family of products. And at the very end, when we come out of all these, you'll get to see what the Series 970B of cold cathode transducer family looks like after all this work was done. All right, so let's get to it. So the first part, we are at PitCon. PitCon is a chemistry conference. At least I'm a chemist. I tend to look at it that way. And vacuum generation is, of course, a standard process throughout chemistry. Doesn't matter whether you're an organic chemist, an inorganic chemist, biological chemist, physical chemist, or an analytical guy. If you're doing chemistry, if you took a chemistry class, even in high school sometimes, you probably did some vacuum work. At least you probably used a water aspirator at some point. Typical techniques in chemistry that use vacuum include vacuum filtration, solvent evaporation, vacuum distillations. If you're a pharmaceutical chemistry or biological chemistry person, you might have done freeze drying or lyophilization. And nowadays, and this is where our focus is very quickly going to go, if you are an analytical chemist, you're probably surrounded by instruments in your lab that use vacuum equipment. And that includes not only just the vacuum instrumentation itself, but also vacuum is becoming a component also in the sample handling or sample management, including things like sample storage, sample preparation, sample activation, and so on. When we now focus on analytical chemistry, modern analytical chemistry is more and more relying on advanced instrumentation. And many of these analytical instruments and even sample handling techniques that happen even before you reach the instrument rely on vacuum technology. And here's a short list of some of the instruments that are commonly found in an analytical lab, an analytical facility today. Anywhere from mass spectroscopy, right, where we got to ionize samples, we got to separate the ions based on mass to charge ratio. Vacuum is required for that. Ion mobility spectroscopy, where we got to move ions right through a drift tube with very controlled gas flow conditions and pressure conditions, and a counter electric field, surface analysis, more and more, Auger, ESCA analysis. Ultra high vacuum conditions are required to make sure that we have very good starting conditions for the substrates. Microscopy, electron microscopes. Without vacuum, we wouldn't be able to deliver those electrons and analyze the energy of those electrons that are emitted. And this even, it's not just all about mass spectroscopy or microscopy. Even in applications like in optical spectroscopy, UV and VUV spectroscopy, where we gotta make sure the photons get there, right? We need vacuum for that because we don't want to lose those photons to absorption through the path. And even gas chromatography too, this is another example where we might use vacuum, for example, for the inlet system, where maybe we are doing headspace analysis, and we got to control carefully how we vaporize the samples. And here on the right side is a perfect example of a analytical instrument. This is one of ours. This is our very own MKS. It's a Cirrus 3XT atmospheric sampling mass spectrometry system, which is a mass spectrometer in its own right, and capable of doing real-time atmospheric pressure gas analysis using mass spectrometers and a lot of vacuum equipment, as you can see on a view of kind of what the guts of the instrument are. And before I launch into analytical chemistry, and the instrumentation needs of the industry, one thing that is very interesting as far as vacuum instrumentation or vacuum measurement goes is that there's been all along a close interaction between vacuum scientists and analytical chemists, which has benefited both disciplines. It's kind of interesting how this has worked over the decades. Improved vacuum technology has allowed us to improve analytical instruments and analytical instrumentation techniques, which in turn has given the vacuum scientists better tools to develop even more improved vacuum technology. And this cycle has continued on and on and on over the decades, making both industries better. And this is one of the reasons why we like to come to Pittcon, because we got to listen to what's going on in the industry, where are we going, so that we can actually help develop through innovation, develop the next generation of analytical instrumentation. Okay, so as we focus now on analytical chemistry and analytical instruments in particular, we like to think of vacuum as surrounding the analytical instruments. And in my view, I typically break down instruments into 5 building blocks. Doesn't mean all of them have it, but most of them have at least some of them. And the way I do this is I present these building blocks kind of in a sequential manner in which the sample is loaded, introduced, activated, separated, and then detected in the system. So we start with sample loading. The sample loading section of an analytical instrument is where the sample is kind of presented to the instrument. This could include a load lock. For example, say you're doing a moldy tough experiment where you got to load in a chip with a bunch of matrix embedded protein samples. You will open up, have a load lock, which is a little chamber. It will have a load lock gate, which will open and expose that chamber to atmosphere. That gate will close. The chamber will be pumped down. And when the pressure is low enough, another gate will open and will allow you to enter that chip into the vacuum system. Typical load lock operation. Of course, that requires vacuum. I got to be able to go from atmosphere to high vacuum, and then be able to expose that chamber to an even bigger high vacuum system without, an inrush of gas and so on. I also have to have a good differential pressure measurement relative to atmosphere. Know what is the pressure of the load lock chamber relative to the to ambient differential pressure measurement, to make sure that when I open up the load lock gate to ambient, I don't get a huge inrush of air into the chamber, which could bring all kinds of problems. So basically, the sample loading section, which requires vacuum, Could be a load lock, could be also a drying chamber where I dry the sample before I bring it into the rest of the vacuum system. Could be a desorption chamber. It might be a DESI experiment or a DART experiment where I'm just desorbing ions by bombarding them with metastables. It could also be the pre-concentrator in a gas chromatography system. From the sample loading, typically, then you go into the sample introduction building block, which is now we're going to introduce the sample into the instrument, and that could be a vaporizer, an atomizer, maybe it's a differentially pumped inlet system, or maybe that's the vacuum chamber itself of the vacuum system itself. But in any case, vacuum is required again for the vaporizer, right? Or for the atomizer, I got to pull on a liquid, right? And I use the differential pressure to pull on the liquid from the sample loading all the way into the sample inlet, right? In a vaporizer, I'm using the pressure the low pressure to get the analyte to vaporize so that I can do an analysis. So once that happens, once the sample is introduced, now what we need to do on an analytical instrument typically is activate that analyte in some way. And that could be ionization, like in a mass spectrometer, where we got to hit the sample with electrons, or maybe with UV photons or BUV photons, or even ions from an ion or an electron gun, in which case I need vacuum to make sure that I don't lose those electrons or those ions to neutral collisions, right? Collisions between electrons and neutrals or ions and neutrals. So vacuum is essential for all these. And even if what I'm doing is just bringing in photons to activate the sample, I still need vacuum in those cases. From the analyte activation block, we go to the analyte separation block. This is where, we have the ions now, we have the photons that we are interested in. Now we got to separate those analytes so that we can do the qualitative and quantitative analysis. And so this could be the mass to charge separator in a mass spectrometer, right? In which case I need vacuum to make sure again that the ions don't get lost to neutral collisions, or I might actually need vacuum to control the vacuum to make sure that I have collisions that allow me to do, for example, chemically induced dissociation. This could also be a drift tube in a ion mobility spectrometer. It could be the electron energy analyzer in a microscopy system, or it could be the inside of a UV monochromator. So again, vacuum is required, and it's required, as you can tell, right, as we go from different sections. Vacuum is required in all of them for different reasons, but it's still needed, and vacuum control is very important. And of course, in some instruments, there is often a dedicated set of vacuum conditions for a detector, maybe because this is a cryogenic detector or very high voltage detector, in which case we have to prevent arcing. No matter what, every one of these stages requires vacuum generation, which could be direct or indirect pumping. And in all of these cases, we need vacuum measurement. And so let's talk a little bit about, since I am a pressure measurement kind of guy, let's focus now on the vacuum measurement requirements. So the way this breaks down in analytical instruments is we kind of have two main areas that we need to concentrate. On the sample loading side, because of the load lock requirements, because of the differential pressure measurement requirements, we typically need to be able to measure. If we are developing instrumentation for this application, we typically need to measure anywhere from atmospheric to high vacuum. And the kind of pressure measurement devices you will find here will be things like capacitive diaphragm gauges, piezoresistive diaphragm gauges, and Pirani gauges. Both absolute and differential pressure measurement are required here for the reasons I told you before, right? Before I open up a load lock port to the atmosphere, I got to make sure that the pressure inside the load lock is not much lower than it is atmospheric, or I'm going to get an inrush of gas, in which case the differential pressure measurement is required. On the rest of the building blocks, typically the measurement is an absolute measurement. Very often these measurements are happening at high vacuum, anywhere 10 to the minus 3 to 10 to the minus 8 torr. If you are dealing with surface analysis instrumentation, sometimes you even have to go into the ultra high vacuum level, 10 to the minus 9, 10 to the minus 11. But also keep in mind that at some point, you got to pump these systems down, right? So at some point, the analyte separation building block will be at atmosphere because, maybe you service the machine, maybe you do the PM, whatever it is. So you're going to pump it down. So it's very common that the gauges that are in every one of these building blocks will include measurement all the way from atmosphere down to 10 to the minus 8 torr or 10 to the minus 11 torr, whatever it is, because you want to be able to track the entire pump down from atmosphere down to what is going to be the base pressure or the ultimate pressure of operation of that section. So this is a piezoresistive diaphragm type technology. You'll find piranha gauge technology. And as we get into the high vacuum, we got to look at ionization gauges. So for somebody in my position where I need to design instrumentation, pressure measurement instrumentation for this industry, one of the first things that we need to understand is what the use cases are and what the requirements are for the industry. And one thing is very, very clear. If we are going to control vacuum in instruments, we got to be able to, you cannot control what you cannot measure, right? So, and one thing that is very true is, particularly in analytical instrumentation, is you need pressure measurement accuracy in order to achieve a consistent vacuum conditions in an instrument. And consistent vacuum conditions will provide you repeatable analytical results in those instruments. And if you have a good calibration curve for that measurement system, then that will lead you to accurate analytical measurements. So you can see the connection here. In reality, any one of these instruments that does analytical measurements depends on accurate pressure measurement in order to deliver accurate analytical results. And that's why the quality of the gauges that you put in your instruments is so important. But accuracy is not all there is to it. For me, looking at the needs of the analytical industry, there are a lot of things that analytical chemists worry about when it comes to their vacuum needs. Pressure range, we got to be able to go from ultra high vacuum to atmosphere, right, with our product line, which typically means the sensors you end up buying will have a multi-sensor, or the gauges you'll end up buying will incorporate multi-sensor integration. We got to be able to do absolute and differential pressure measurements. In fact, you'll typically end up with gauges that are specialized for the type of measurement that you need to do. You can buy load lock gauges, for example, that take care of the automation of your load lock. Footprint is very important, or size is very important. Instruments are getting smaller. Our gauges have to be able to fit into those instruments. And so that means modular gauge design is becoming increasingly popular, and particularly modular gauges with multi-sensor integration. I'll talk more about what that is. We talked about accuracy, how important that is. What that means to us is that it's not good enough for us to just build a gauge and assume it's going to work for you. Factory calibration is a must. Field calibration should be available. And of course, many laboratories looking for good laboratory practice kind of certification, they will need traceability as well. Reliability is important. We want minimum preventative maintenance on the gauges that we use, which means for us, we got to look at the kind of analysis being done, make sure that we are chemically and physically compatible with the measurements that are being performed in the analytical instrument. Of course, the analytical industry wants serviceability. Low maintenance requirements are very important. There is also very specific mounting, gauge mounting and wiring requirements that are developing in the industry, and we got to be able to take care of all of those. There is an increasing demand for smart functions, built-in self-diagnostics. It's good to know that something is about to break before it breaks. And some gauges eventually will fail. That's just the nature of the technology, just like other parts of your analytical instrument. And it's good to know in advance, before the failure happens, that it's about time to do a PM or a service. And of course, we are, as instrument manufacturers or vacuum instrumentation manufacturers for the analytical chemistry industry, we got to pay attention to cost of energy. We are continuous pressure from the OEM instrument manufacturers to do cost reductions, which for us is great because it gives me more reason to be with the need for continuous improvement, and in manufacturing also innovations in the R&D lab. Okay. So what it means for us, for MKS, looking at the analytical market, is that when you look at our product portfolio for analytic, we end up with a very extensive portfolio. All the products that you're going to be looking at, most of them are of a modular design. And when you look at it, it can be a little overwhelming because there's so many options. You have dedicated gauges like this load log gauge up here. You might have single sensor devices. Here's an example of a micropirani sensor, an absolute piezo sensor, a dual sensor with it's multi-sensor technology, and all the way to multi-sensor technology. These are high vacuum gauges, and of course, since we service also surface science instrumentation or high-end mass spectrometry instrumentation like an FTICR or an Orbitrap, we have to offer ultra-high vacuum products as well. Bottom line is you end up with a very, very wide product range, lots of products. And what we're going to do today is we're going to focus on the Series 900 transducers, which I kind of circled here with a green ovals. These products, these transducers, are all of a modular design, which means that in a small little package, they include the sensor on one end and the electronics on the other end. And they're true transducers. Gas comes in with its pressure, and a pressure signal comes out. All you have to do is mount it on the vacuum system, apply some power, and a signal comes out, which you can choose. You can pick up an analog signal or a digital output from these devices, and this is how you get your pressure measurement. Okay? And as you can see, here's the pressure range. We cover a very wide range, all the way from ultra-high vacuum to atmosphere with these small devices. Okay? When you look at the Series 900, you're looking at a wide pressure range. As you're going to see, a lot of MEMS technology facilitated the small package we're looking at. There's a lot of sensor integration where you have more than one sensor at a time inside one of these gauges. Products that are able to do both absolute and differential pressure measurement. And because of this wide range of capabilities, well suited for the analytical industry, we are today the market leaders for that market. So anyways, here's a list of all the products which we're going to be talking about today. We'll talk a little about the 925 micropirani. We'll talk a little bit about the 902, the 901P, the 902B, the 910, and then we'll spend a lot of time talking about the challenges of incorporating cold cathode gauge technology into this product line. All right, so let's start. When we started with the 900 series, the first thing that we did was we focused on rough vacuum measurements, anywhere from atmosphere to 10⁻⁵ torr, and we were able to take care of MEMS technology sensors at that point. So here's a perfect example of the very first 900 series product that we released. This is the 925. This is a modular transducer again, right? So apply power, bring the gas in, and then a signal comes out. So we transduce pressure into a voltage or pressure into a digital signal. In a very, very small footprint, you can actually see this guy pretty small, 1.93 inches for a KF16 flange. It's capable of measuring pressure from 10⁻⁵ torr to atmosphere. And the reason it can do that in such a small package is it benefits from our very own micropirani sensor, MEMS micropirani sensors, which is quite an advantage over traditional Pirani sensors, which rely on a single wire, because by being a little modular, tiny little chip as it is, its resistance to vibrations, also very resistant to air inrush. And on the right side here, you can kind of see what the MEMS sensor that is inside this device looks like. That's a TOA header, which is smaller than a penny, and inside of it, or in the center of it, is the Pirani sensor, which right here on the bottom, you can kind of see what it looks like. It's a 5mm by 5mm chip, and the actual active sensing element, the heated wire or heated sensor, is right here in the center, which is blown up here, and it's just a nickel sensor wire on a silicon nitride membrane. Such small sensor is what makes it possible to make such small controllers. We were able to take care to use MEMS technology also in the 910P, which is a combination of both a micropirani and a absolute piezo sensor. And again, this is a very small device. This is a MEMS device. And the advantage of this device is that now we combine in a single sensor a MEMS micropirani and an absolute piezo sensor, which comes with a stainless steel encasing in it. And because of the stainless steel case, we have a very large chemical resistance. So it's a great product to use to increase the accuracy relative to the Pirani sensor above 10 torr, and also if you're going to be exposed to high pressures of reactive chemicals that might actually interfere with the hot sensor wire. We were also able to use MEMS technology as we move forward to develop a first of its kind load lock vacuum transducer. Same size. Look, we haven't changed yet the size of the product, right? This was the early stage, same package as the 925. This one does both absolute and differential measurement. And it takes advantage of the micro-Pirani and also a MEMS piezo differential sensor. And this device is not only a pressure transducer, but also contains all the signal, the I/O that is required to control a load lock. And you can see here on the right side, kind of it all comes together in a cross section. On the right side is the Pirani sensor. The Pirani sensor can measure all the way down to roughly 10⁻⁵ torr. So this is the one that will give us the information that we need in order to say, okay, we are low enough in the load lock to open up the gate and bring this sample into the rest of the vacuum system. But it also includes a differential PRD, which can measure the difference in pressure between atmosphere and the load lock. And this is the sensor that will tell us whether we can open up the load lock gate to the atmospheric, to the ambient atmospheric pressure, so that we don't have an inrush of gas in the system. So really nice, small, compact load lock, first of its kind sensor, which took advantage again of MEMS technology. And by the way, same thing that I was talking about before, where we have this fun interaction between vacuum technology and analytical chemistry, where we both benefit from each other. Same thing is true for MEMS. Those MEMS sensors that I described are all made in vacuum chambers too. And so there is, again, this feedback mechanism, right, where we are improving our vacuum technology, improves the MEMS manufacturing, which provides us better sensors to improve our vacuum technology and so on. So funny how that works, right? So anyways, everything was going pretty good when we started the 900 series. We had the advantage of the MEMS sensors, but then things got a little more complicated when we decided to go into high vacuum and still keep a modular package. Our goal was to go into the 10⁻⁸ torr limit with industry-leading accuracy, but there are no MEMS sensors there that can do this. The only thing that can do this is ionization gauge technology. So there were two things that we had to resolve very quickly. Which ionization technology is best, and how small can you go? Can we keep this small form factor and still provide you with a accuracy-leading ionization gauge for your analytical instrumentation? Well, the bottom line is I'm giving you the answer already. Yes, we were able to do this. We developed a 97X cold cathode gauge transducers family, which can cover all the way from 10⁻⁸ to atmosphere in a single sensor or multi-sensor configuration, including a version that includes load lock handling capabilities. So what I want to do now is kind of talk to you a little bit about what it took to get there, right? So this is more of the technical part of the talk. First thing that we had to do was to decide what kind of ionization gauge technology we were going to use on the 900 series. And there are two kinds. There's hot gauges and there are cold ionization gauges that you can use for this technology. We knew that both of these technologies could achieve the minimum reportable pressure of 10⁻⁸ torr. We knew that these two technologies could be used in a multi-sensor integration package, had already been done. We had done it already, not in this small scale, but we have done it in other instruments. We also knew at that point that hot cathode ionization was known for showing better accuracy than cold ionization. So we gave cold ionization a yellow here in the risk, right, department. We knew that hot cathode gauges could be miniaturized. All you have to do is look at our micro-ion gauges, and you'll see you can make very small ionization gauge, hot cathode ionization gauges. We didn't know how small we could make the cold cathode gauge at that point. We also knew that hot cathode gauges have very little physical interference with the measurement, whereas cold cathode gauges having magnets in them could have more interference with the measurement, so we gave them a yellow. But then by the time we got to things like outgassing levels and lifetime, we knew that a cold cathode gauge was going to outperform a hot cathode gauge in these particular applications. So the question that, and this red is, kind of a showstopper. Yellow means maybe we can do something about this, right? So as we moved on, deciding what we're going to do with the 900 series, the first question we asked ourselves was, can we flip these yellows for cold cathode gauge technology into greens, turn everything into greens, right, and provide a cold cathode, modular cold cathode gauge with a 10 to the minus 8 torr reportable, minimum reportable pressure, a very wide pressure range through sensor integration, industry-leading accuracy, is the smallest of its kind ion source design, a low magnetic field that wouldn't interfere with analytical measurements, and at the same time give you the advantage of the low gassing and the long service time. So that's the challenge that we had to go through. And what I want to do is kind of talk to you a little bit about what we had to do to get there. And to do that, the first thing I have to do is kind of show you how a cold cathode gauge works. So a cold cathode gauge basically includes a cross and magnetic electric fields in a ionization region. And as one of my old bosses used to say, a cold cathode gauge is simply a post in a can. And in that post in a can, we develop what is called an inverted magnetron discharge. The idea is very simple. We have an anode in the center. This is a cylindrical symmetry chamber. We have an anode. That anode gets biased to positive high voltage. We have a cathode at ground. So when I bias this anode, I get a radial electric field. We also have a magnetic field, which is a cylindrical magnet in this case, that is axial. So we have a cross magnetic and electric field. And when we apply high voltage to the anode, a discharge is established. It's called a Townsend discharge. And the discharge current that flows through this chamber is the measurement of the pressure in the system. That's how cold cathode gauges work. The reality is, in order for a cold cathode gauge to work, you need both the magnetic and the electric field. If I took the magnet out and I just turned the anode on and I put an electron here without the benefit of a magnetic field, the electron will simply go to the anode and it get lost. No discharge would get established. So you need a magnetic field for this to operate, right? And in this case, if you add the magnetic field, this is an actual molecular simulation, right, with a electrostatic modeling program. If you actually throw an electron and you have a radial electric and an axial magnetic field, the electron will start precessing around the anode. Okay, so what you end up with here is electrons trapped in precession. A pure electron plasma develops, and in this pure electron plasma, you have electron energy enough to produce ionization of molecules. You look at it from above, it looks something like this. You have an electron sheath, right, of electrons precessing around the anode, as long as the high voltage is on, and you put the magnet in. And I cannot tell you how many times I forgot to put the magnet in and go, why don't I have a discharge? But anyways, this sheath of electrons here is actually a pure electron plasma. And as the electrons slowly start interacting with the neutrals and producing ions, they lose energy and eventually drift towards the anode, and new ones need to come in. So how does the gauge work? Well, we have our electron cloud, which is essentially an ionization region. If a gas molecule comes in and crosses that electron cloud, it gets ionized. And as soon as it gets ionized, the electric field pushes it to the wall, where it gets picked up as an ion current. So I-ion is an electron, is a ion current, is a discharge current in the discharge, which is, as we're gonna see, proportional to the gas pressure. And of course, what happens here is because we have such long electron trajectories in this device, we have very, very high sensitivities that allow us to measure pressures with cold cathode gauges down to 10⁻13 torr if you want. Of course, that's gonna require much stronger magnetic fields that wouldn't be compatible with a analytical instrument, but it can be done. So anyway, this is kind of how it all boils down. The gas molecules enter the pure electron plasma and get ionized. The ionization rate is proportional to the gas density. And the magic of the magnetron discharge is that if you do things right, this electron density is independent of pressure. And if it's independent of pressure, then the ion current is linearly related to the pressure, which is great. And so literally, when you look at how you calculate pressure with an ion gauge, the pressure is proportional to the ion current, and there is usually a coefficient N there. And K here is the sensitivity factor, ion is the discharge current, which you measure with an electrometer, and N is the linearity of the device, which you want it to be as close to 1 as possible. If it's close to 1, you know that your electron density is independent of pressure, and you get a much better calibration out of this device. Unfortunately, there are challenges when you make a cold cathode gauge. The two known challenges, particularly if you're trying to get high accuracy, are you got to achieve this linearity, right, on the performance, and you also have to avoid what's called discontinuities. What ends up happening is, going back to this pure electron plasma, depending on the voltage and magnetic field conditions in the system, sometimes the cloud can actually switch to a different spatial mode. And when it switches to a different mode, the sensitivity of the gauge changes, and you get these steps in sensitivity, which affect the calibration. So particularly in this area here, you really don't have a good way to calculate pressure if you get a step down in the ionization. So a well-designed cold cathode gauge needs to have a lot of linearity, and it has to have no discontinuities. Okay. Also, non-linearity, I say here, relates to ignition problems. So often, if your linearity is no good, your ignition pressure is also much higher, and you can run into trouble. For those of you looking at why this curve turn around, you always put a limit to the amount of current that can flow in a cold cathode gauge so that it doesn't sputter itself away. So the jobs to be done, as we looked at the cold cathode gauge technology, right, we had to work on a gauge design that was free of discontinuities, that had good linearity, a lower ignition threshold below the 10 to the minus 8 that we wanted to measure. We also knew that to get the accuracy, we were going to have to work on an enhanced calibration procedure, a factory calibration procedure, and very likely revamp the way in which we did pressure calibration. We also knew that we had to push the envelope of how small we could go with the gauge. And we also knew that we had to keep the external magnetic field really low. So there were a lot of things, a lot of variables that we had to tweak in order to be able to get to the cold cathode gauge design that would provide all the features that we were looking for. This is a very long laundry list of things that you have to look at when you're trying to do R&D in a lab. So I'm going to just, I'm not going to go obviously through all of those. We don't have time. You probably don't want to hear to all of them. But early on, even with the early prototypes, we had a lot of early successes. From the mechanical point of view, we were able to make a small ionization chamber. We were able to do the multi-sensor integration. We were able to do all this with a single piece cylindrical magnet, and including a field replaceable cathode in the device. In terms of performance, we were able to achieve no discontinuities, a very linear response. We were able to achieve ignition pressures lower than 5-9 torr, which was a requirement for 1-8 minimum reportable pressure, which also allowed us to incorporate a first of its kind discharge detection mode, which is very important for you to know that things are going well. We were able to do this with a reduced external magnetic field, while at the same time providing, and this relied a lot on this enhanced calibration procedure, industry-leading accuracy, a very fast discharge start, and we even threw in a low temperature pressure measurement compensation algorithm into the mix. In terms of calibration, we developed an enhanced calibration and verification procedure. I don't believe anybody else in the industry even knows how to do this today. So this procedure includes both 4 basic steps. First, we do a calibration followed by accuracy verification. Discontinuity tuning, we make sure that every gauge that ships to a customer is free of discontinuities, which is critical for accuracy. We do a linearity check on every product that we make, and we also do an ignition threshold check on every product that we sell. And while we're at it, we redesigned the way in which we did the pressure calculation so that we would have flexibility to do changes if we wanted to the design and not have to completely redo our firmware and software that is built into the instrument, while at the same time also providing a seamless transition between the sensor technologies. So this was all great. And everything was going great even in the early prototypes. But what I want to talk to you is one example of something that suddenly went wrong towards the end. And that is, we had been working all along with prototypes, right, where we had a very good performance using handmade electrical feed-throughs to attach our anode to the cathode can. Remember, the post in the can that my boss used to talk about. But we knew these were all glued together with an epoxy, high vacuum epoxy, high quality. But we knew that by the time it was supposed to become a product, we were going to have to go to an all metal design, which meant a brace feed-through. When we put the brace feed-through in, thinking this is going to be the greatest thing since sliced bread, suddenly we lost performance. Sensitivity went down, less than 1 amp per torr. We lost linearity. The N value started to go higher than 1.3, and our ignition threshold became really bad. We were scratching our heads. What's going on, right? We tried a bunch of different things. We tried material changes, different designs for the feed-through and so on. And in the end, it really became apparent that there was something much more subtle going on. And our basic assumption became that it was this additional washer that is typically thrown into feed-throughs that was causing the headaches for us. It's very common, right, in a braced all metal feed-through to incorporate a little washer on top that is completely braced onto the ceramic and onto the anode. And that is a big part of the vacuum hermetic seal, right, that these feed-throughs provide. So our assumption became that it was this braced metal washer that was responsible for the performance degradation. This metal washer, our assumption was that, our explanation or root cause, was that it was really affecting the boundary conditions of our electric fields, and it was compromising the discharge. So we started doing a bunch of electrostatic modeling and so on. And pretty much what it came down to, what we realized was that in the case where we had a homemade feed-throughs with no metal washer on top, the electric field was very well behaved, and it behaved radial over the entire length of the electron discharge. It's kind of what you see here. So what it means is the electrons would precess around the anode, but if they tried to get close to the feed-through, they couldn't, right? And they would just turn around and be very well constrained. Unfortunately, when you added this little washer into the system, now you disrupted the electric field. So right close to the end at bottom here of the anode, the electric field was no longer perpendicular to the magnetic field. In fact, it was no radial anymore. It had a axial component. And because of this, electrons could actually get lost to this washer. You can actually see it right here, right? The electron is precessing, and now it can go down here. This by itself can cause a lot of trouble. Just having this little loss, particularly as you lower the pressure, what happens is as your rate of replenishing electrons, which comes from secondary electrons from the cathode when the ions hit the walls, as the rate goes down, this loss of electrons can actually make the electron cloud lose density as the pressure drops. When you lose density when the pressure drops, that means that now you have two things that change linearly with pressure, and so now you no longer have a linear response between the pressure and the ion current. So the models suggested this is exactly what is going on. It all made sense. We had a very good explanation. We had bad boundary conditions, right, for our pure electron plasma. We had to fix these. The solution we came up with was very simple. This is what we call an anode electrode shield. So we added a little shield around that washer at ground, connected to ground potential. This is actually a patented solution. The way this shield works is pretty simple, right? Whereas in the previous design, we had electrons that could actually be lost to this washer here on top of the anode. In the case of the shield, since this shield is sitting at ground, if an electron tries to get close to this anode washer, it will encounter mostly a ground potential, so it's actually going to go and turn around, right? An electron, sorry, if an electron tries to get close to the anode shield, it's going to be rejected by the ground potential, and it's going to turn around. I'm going to have a much better defined boundary condition for the discharge and a much better defined pure electron plasma. When we did this, what we actually found was that not only did we solve the problem that we were seeing with the feed-throughs, but we actually overshot. We had even better sensitivity than we had in the original prototypes. We actually had about 8 times more sensitivity than the original prototype, which was great. We improved the linearity. We don't ship product that has a linearity higher than 1.1. We lowered the ignition pressures. We also increased the gauge lifetime because this shield also provides a mechanical protection for the feed-through. So any material that gets spattered off the walls that could coat this feed-through and provide leakage current, which affects accuracy, now is shielded by these anode shields. So we actually found enhanced lifetime in this gauge simply because of the addition of this anode yield. And because the boundary conditions are now very well defined, there is no charging in the feed-through that we have to deal with anymore. We also found that we have improved gauge-to-gauge reproducibility, so we have a much more consistent product. So the bottom line was with this, with all these early successes, the surprises we had along the way, we were able to incorporate cold cathode gauge technology into the 900 series sensors, and this is what led to the MKS series 970B with cold cathode transducers. There are 3 versions of them, 3 product versions of it. That allow us to have a wide pressure range, keep the small footprint, very reliable, provides the serviceability that we're looking for. Cathode gauge is a perfect example of that. Very easy to operate. Basically, you mount it, apply some power, and look at the analog or digital output, and also a lot of built-in process control I/O. And there are 3 products: 971, which is the simple cold cathode gauge; the 972, which is the cold cathode with the MEMS micropyramid we were talking about, which allows you to measure all the way to atmosphere. You can also follow that here on this graph. And the 974B, which is now a combination of the cold cathode, a micropyramid, and a differential PRD that allows you to follow pressure all the way from 10-8 to atmosphere, while at the same time providing you load lock capabilities. And in this picture here, you can kind of see how it all came together. This does not include the picture of the anode shield. It's an earlier version of the drawing, but so the anode shield just kind of sits right here. And you can actually see the multi-sensor implementation, how easy it is to do this thanks to the MEMS integration. So as a conclusion, I hope that this kind of gave you an idea of what the amount of variables and the amount of work that goes into the development of a product line for any industry, for that matter. In this case, in particularly for the analytical market. So as conclusions, I wanted to bring back up the idea that consistent vacuum conditions are required, to get repeatable analysis results in modern analytical instruments. To get repeatable or vacuum conditions, in other words, to have good vacuum generation and good vacuum control, you have to have accurate and stable pressure readings in your systems. So pressure measurement is critical. And the other thing too that is in analytical instruments, and the thing that we have to realize as pressure gauge manufacturers is that analytical chemists have very specific vacuum gauging requirements with a very broad range of use cases and measurement techniques. There are a lot of things we need to pay attention to, right? The needs of an analyst using an orbit trap are very different from those doing an LCMS experiment. And somehow we gotta be able to take care of all of them. So hopefully by looking at the 900 series, you're starting to realize that MKS today provides the most comprehensive and innovative vacuum gauging portfolio for the analytical chemistry industry. And also, I want to bring up one more time this fact that there is this constant interaction between vacuum science and analytical instrumentation, analytical chemistry going on, which we hope will continue moving forward. And it is actually one of the reasons why we come to Pittcon. We want to hear from you. We want to hear from chemists, what they need, what you need, so that we can keep innovating and making products that are best suited for your applications.